So if a constant force Fnet acts on a mass m through displacement delta s, we can determine the change in the quantity mv squared. And we could. And so if we find the change in mv squared, we can find the change in 1/2 mv squared, okay? And maybe I wanted to state it this way. Either way, it's very similar. You use exactly the same reasoning. So, what do we know? If we know Fnet, m, and delta s, what can we do? Well, Fnet and m will give us acceleration. So, once we know the acceleration, then we have delta s. Well, acceleration is the derivative of velocity, and velocity is the derivative of position. And just knowing acceleration and delta s, we don't really know enough to draw any conclusions, but we can still go to the third equation of motion, fourth equation of motion, uniformly accelerated motion, which is this. And in this situation, we know A and delta S, so we can calculate this quantity. Now, this quantity is going to be equal to what? Well, this quantity minus this one. So A delta S, if we just solve for A delta S, we get, and the algebra is very straightforward, you should understand it very easily. Just isolate A delta S, subtract V naught squared from both sides, and then divide by 2. This is what you get. You get 1/2 VF squared minus 1/2 V naught squared. And this is the change in the quantity 1/2 V squared. And what we're trying to find is the change in the quantity 1/2 mv squared. In terms of Fnet and m, well, it then follows that A delta S, since A is Fnet divided by m, we can replace A by Fnet divided by m. So we have Fnet divided by m times delta S is equal to the 1/2 VF squared minus 1/2 V naught squared, the change in the quantity 1/2 V squared, so that Fnet delta S is 1/2 mVF squared minus 1/2 mV naught squared, and that is the change in 1/2 mV squared. So the answer to the question is, the change in 1/2 mV squared is just Fnet multiplied by delta S. So that applies, and we don't have to know what the mass is. If we want to find the change in the 1/2 mV squared quantity, we don't have to know the mass, we don't have to know anything about the velocity. We just calculate Fnet delta S, and that will be it. So, for any mass, Fnet delta S is the change in the quantity 1/2 mV squared. Now, we don't know anything about V. Doesn't matter. I mean, it's going to matter. We can use this to draw conclusions about V if we know some things about velocity, but we don't have to know this. We know that this has to equal this. Okay, well, we call this quantity the work done by the net force as we go through the displacement delta S. And this is the change in what we call kinetic energy. Kinetic energy being 1/2 mV squared. This is the change in 1/2 mV squared, and this 1/2 mV squared is the thing we're going to call kinetic energy. So, we have a definition of kinetic energy. If you have a mass m moving at velocity v, kinetic energy is 1/2 mV squared. Now, you maybe ought to think about what the units of that would be, and what the units of Fnet times delta S would be, and verify for yourself that they have the same units. Hopefully you would spontaneously do that. But, yeah, you might not think of it. It's kind of a new thing, so it's not a big deal if you don't. Still, good exercise. I recommend it. Okay, well, now we're going to apply this to just one situation, and it's not the simplest situation, intentionally so, because if the first thing you see is the simplest situation, you're going to want all situations to be that simple. This is not a difficult situation, but it's not as simple as the oversimplified situation you usually see first.